So how does this work? What determines whether something responds elastically, plastically, or brittly? Well, if we go all the way down to the atomic level, that's where we can see what's happening. Atomic bonds are at specific angles. Within a molecule, each atom is arranged a certain way, and the atomic bonds have preferred angles and orientations. Well, sometimes when you apply stress, they get flexed a little bit. If the bonds bend to new angles but don't break, and the molecules aren't shifted past each other, they're just, again, the connections between the molecules are stressed, or strained rather, without breaking, so just bending to new angles. This means that when you remove that stress, since no bonds broke, they will revert to their preferred angles. It's like if you have a ruler and you have it sticking off the edge of a desk, and you're holding it down firmly with one hand, and then you press on the other hand, or on the other end of it with your other hand. The ruler's preferred orientation is straight out from the desk. If you push down some, it flexes. You let go, it returns to being straight. That's like one of the atomic bonds. However, if you push too hard, it'll snap the ruler. As long as you don't break it, then you're going to get elastic behavior. And it's because at these specific angles, the molecule is at its lowest energy, its happy place. Now, how quickly it reverts to that low energy, happy place condition depends on the material. That rubber band or that bungee cord, it's pretty darn fast, sometimes dangerously fast. The Earth's crust, really, really slowly. Now, bonds have a limited range that they can flex. Different bonds have different ranges, depends on the molecule. But if they flex too far, they will break. It's like the rubber band. If you pull it a little bit and then let go, it'll spring back. If you pull it really, really far, it'll break in half. It's never going to be the same again. You can't release the stress and have it rejoin back into one piece. It's broken. That's brittle behavior. Now, I mentioned the moduli. There are 5 of these that you need to worry about. These are things you want to write down in your notes, in your notebook. They're in the textbook, but these are very, very important. They will be on the test. They will be later in life when you're working in geology or even engineering. A lot of these show up in a lot of engineering applications. Young's modulus, Hooke's law, shear modulus, bulk modulus, and Poisson's ratio. These are the 5 moduli and equations that are central and pivotal to understanding how material deforms under stress. So we'll look at them one at a time. Young's modulus, represented by capital E, is the ratio of stress to strain. Basically, how much strain happens for any given amount of stress. And the equation for Young's modulus is sigma over epsilon. Sigma is the applied stress, specifically compressive. So if it's tensional stress is equivalent to negative compression. So if you have tension, you have to have a negative sign in front of your sigma. Sigma is in the compressive direction. In geology, remember, compressive stress is positive. I know, opposite for the engineers or physicists, but in geology, compression is the most common stress you'll find anywhere in the world. So geologists use positive value for compressive stress. Now, epsilon, the little curly rounded E, is the resulting longitudinal strain. So this is in one direction. It's just longitudinal. It's rather important. Again, think of the rubber band. You're pulling in one direction, it's changing in one direction. Now, Hooke's law, sigma equals E epsilon from Young's modulus, is basically the same exact thing as Hooke's law. But the terms are slightly different because we're dealing with restoring force. The restoring force is precisely the opposite of the stress that created the deformation. So it's like when you look at Young's modulus, you're pulling the elastic band, the rubber band. When you let go of it, that force that's pulling it back together is F in Hooke's law. K is the spring constant, equivalent to the elastic modulus, Young's modulus. And X is the displacement. Now, because the restoring force is the opposite of the stress applied, we have a negative sign in here. We don't have it in front of the F because when you set up an equation, you always want your value isolated. So you move the negative sign to the other side, and you have F equals negative kx. That's Hooke's law. Also used for springs and other things in physics. Now, the shear modulus, capital G, is used to explain the deformation of a solid by simple shear. And it's the ratio of shear strain, gamma, to shear stress, sigma, with a little s subscript, so we know it's specifically shear stress. Sigma by itself, compressive stress. Now, the shear stress is that force per area being applied in a shearing manner to our object, this dotted line square. If we see what angle it deforms to and take the tangent of that angle, we get gamma. Remember, the angle is psi, tangent psi is gamma, which is shear strain. So the shear modulus, capital G, ratio of shear stress to shear strain. Bulk modulus, K, think of it, bulk has a K in it, it gets the K, is the ratio of the volume change and the compressive stress in all directions. When stress is equal in all directions, all three axes, remember we call it an isotropic stress. This is the same as like hydrostatic stress. If you submerge something in water, the pressure is the same on all sides. That's where we get the whole hydrostatic pressure or hydrostatic stress term from. And when it's the same in all directions, isotropic. This will cause a volume change. Remember, isotopic stress, volume change. Deviatoric stress, shape change. So when we have this general pressure, whether it's increasing the pressure or decreasing the pressure, a volume change can occur. Some materials are incompressible or nearly so. A lot of materials will change size. Now, in this case here, we have the term delta. In the denominator, it's by itself. It's a special term. Delta, when it's not, has no letter with it, is volume final minus volume initial divided by volume initial. If we didn't have that divided by volume initial, we could just say delta V for delta volume. A lot of times that's what you're used to seeing. As soon as you are dividing by that initial volume, delta by itself. So we have delta P in the numerator, change in pressure. So pressure final minus pressure initial. That's our numerator. The denominator is delta, where you have volume final minus volume initial divided by volume initial. So K equals negative delta P over delta. If you look on page 95 in your textbook at table 5.3, you can see some stuff about bulk moduli.